I was trying to think of a theme. This is preaching to the choir about nano. I was trying to think of a theme that I would focus on. So I decided to focus on things that are unique to nano that you may not see at the macro and micro scales. There are a number of phenomena since the National Nanotechnology Initiative was started in the US when President Bill Clinton announced it at Caltech around 2000. Many, many discoveries have been made by large numbers of scientists, and many new phenomena have been identified only at the nanoscale. So what I would like to focus on are phenomena that are unique to nanoscale, and I define nanoscale in two different aspects. Large structural materials, where the smallest characteristic microstructural dimension is of the order of nanometers or tens of nanometers, or systems whose dimensions themselves are only nanoscale, tens to hundreds of nanometers. So I would like to focus on those two systems. So the outline for my talk is as follows. I would like to start with listing a few of the things that are unique to the nanoscale, then focus on mechanisms that are activated at the nanoscale, and then I will finish with, most of this talk will focus on advanced materials, material science, but given my path over the last 15 years, I would like to end the talk with one example where nanoscale features play a very important role in disease diagnostics, precision medicine, and liquid biopsy. So I would like to end the talk with that particular example. So what are some of the things that are unique to nanoscale? There are many, and I cannot list them all here. I'm just going to focus on a few of these. Of course, we have very high surface to volume ratio, low defect density in many of these systems, and proximity of these defects to free surfaces, limited number of defect nucleation sources, such as Frank-Reed mechanism for dislocation, multiplication, etc., inhibition of defect nucleation sources, typically with decreasing grain size, very rapid increase in strength through Hall patch type mechanisms, and of course as the grain size approaches very small dimensions, the so-called inverse Hall patch relationship. Typically, increase in strength is accompanied by low ductility, toughness, damage tolerance, and resistance to fatigue crack propagation. Greater environmental susceptibility and possibly toxicity as well in some cases. But there are also some advantages of nanoscale structures. We showed a few years ago that if you take single crystals of, say, a single crystal of aluminum, the mere act of mechanically cycling it at room temperature so that you impose a stress that's large enough to unpin dislocations and move them close enough to the surface so that the image forces can attract them and take it out of the system, but not large enough to create new additional dislocations, can lead to healing of the material, which is essentially a beneficial fatigue effect due to cyclic loading. Elimination of defects due to mechanical loading in certain nanosystems under certain conditions. There are a number of gradient architectures that one can create with nanostructures, not all of which have yet been tried in research, which have potential for significantly transforming material design and surface design, and I'll show some examples of this. And of course, many, many more. One of the nice things about the nanostructures and nanoscale materials is that combined with advanced additive manufacturing techniques such as 3D printing, one has the opportunity to create unique new architectures and materials that are digitally designed, involving both computational and experimental approaches. And I'll show some examples, not through 3D printing, but that can potentially be applied through 3D printing as well. So rather than going into general things, I thought I'll focus on a few examples and go into them in sufficient detail. Since we are in Hong Kong, I'm really delighted to show the first example, because this is some very recent work from a couple of months ago, where in collaboration with colleagues from the City University of Hong Kong, we showed some phenomena in diamond which can only happen at the nanoscale. So essentially, bending of diamond at the nanoscale. So colleagues at the City University of Hong Kong, here the names are listed here, Professor Zhang and his co-workers have been working on nano diamond for quite some time. So if you take a silicon substrate and deposit a thin film of diamond on top of it through plasma-enhanced chemical vapor deposition, and then you use etching to create needles where the height of the needles is of the order of 200 or 300 nanometers, and the diameter is probably less than 100 nanometers, you create many of these diamonds on a substrate. We all know that diamond is the hardest material found in nature, and it's very difficult to deform the diamond elastically beyond a small amount. Typically, when you go to a strain of as small as 0.15, 0.16%, diamond undergoes catastrophic fracture. It has high strength, of course. So is it possible under nanoscale to deform diamond to sufficiently large reversible elastic deformation that cannot happen under micro and macroscopic conditions? So that was the fundamental question. So we decided to try this by using some of the latest tools that have become available in the last 10 years, 10, 15 years or so. So we take this diamond needles on a substrate inside an SCM where we can use a diamond tip in a nano indenter to either push it down or come sideways and bend it and see how much it bends. And we can try to impose different amounts of controlled elastic deformation. Of course, there is anisotropy. There is the potential for nonlinear elastic deformation. With the computational tools that are at our disposal, such techniques as finite element method, where we can model elasticity reasonably accurately, we try to interpret, first experimentally show how we can deform diamond, and try to interpret through analysis what the maximum strains are. And using these, we try to understand the mechanisms. Now, why would we even expect or hypothesize that there is the likelihood of large elastic deformation in diamond? First of all, at the nanoscale, if you can create pure surfaces, the possibility of defects in diamond are relatively small. The possibility of in single crystals and in very small volumes, the possibility of creating smooth surfaces and defect-free materials is large. So maybe there is an opportunity at the nanoscale that we are able to deform diamond. So here is the microstructure that was produced. In your top left, you see the indenter coming down, and there is a large number of nano needles that are sticking out of a substrate. On the right-hand side, you have a high-resolution TEM image of the surface of diamond. In figure B, you see the diamond tip, like an AFM tip or a nano indenter tip, coming down to push one of the diamond needles. Figure C shows a schematic of how that happens. And then, of course, if you push it far enough, diamond will catastrophically break and you'll get a brittle fracture surface. You can take the orientation of the fracture surface with respect to the crystallography of a single crystal, and you can demonstrate that this is a classic brittle fracture process that takes place. So here is a series of still images from the videos that were taken in the experiment showing how the diamond deforms. This is in a single crystal. So in the top row, as the indenter tip comes down and starts to deflect the diamond, you can see the diamond being bent, the needle tip being bent. And if you don't reach a critical threshold value of stress or force, but you retract the diamond tip, the needle goes back to its initial shape. And that's what happens in the top row. In the bottom row, if you do the same thing, but exceed the point at which fracture is initiated, you see the catastrophic fracture in the middle of the figure, in figure B3, where you see the diamond needle being catastrophically fractured. And you see the fracture surface in B4. Figure C shows the load displacement curve for this failure mode of pushing diamond. You see an elastic response. So the blue data points show the deformation before catastrophic fracture. So we unload it, we go back, and then we reload it. You see a little bit of hysteresis because of friction between the diamond tip and the nano needle. But if you redo the experiment after unloading, if you reload the same nano needle, you see the red curve. And in the case of the red curve, we go all the way to the point of fracture where the diamond catastrophically fractures. To your extreme right is the finite element simulation that takes into account anisotropy and nonlinear elasticity. And what is plotted here is the maximum elastic strain. And in this case, it's a tensile strain in different colors. The maximum point on the tensile side of bending, the strain is of the order of about 9%. So essentially, with diamond, we can deform it in the nanoscale that you cannot do at macro or micro scale locally to a maximum strain of up to 9%. That's what this shows. Now you see that in video, both experiment and simulation. So when you do a large number of these repeat experiments in single crystals, and I mentioned that there is a little bit of friction. So we did, in our computational simulations, we tried to understand the effect of friction on the strength that we get. So what is plotted here is maximum elastic tensile strain for single crystals under two different conditions. Elasticity refers to deformation without fracture, where we unload. What is the maximum stress, maximum strain we can get, tensile strain we can get without fracturing? And in the case of specimens that fractured, what is the maximum tensile strain? Of course, when we create by etching diamond needles like this, there is a variation in geometry, there is a variation in friction, there is a variation in height, etc. So it's not surprising that you get quite a bit of variability in experimental data. So what you find is that the maximum elastic strain in the single crystal case is between 4 and up to 9%. We also did experiments in polycrystalline diamond where the scatter is much smaller, and you can see the data for elasticity, and in the case of fracture, for a friction, so we did two friction coefficients, 0.1 and 1.0, and in both cases, in the case of polycrystalline diamond, you get a maximum elastic tensile strain of about 3% or so. For comparison, bulk diamond has a much, much lower tensile strain as expected. We also did density functional theory and molecular dynamics calculations of stress strain curves. So what is plotted in black is the stress strain curve from a DFT MD calculation, where we found that the maximum tensile stress is of the order of about 140 GPa, and the tensile strain at which fracture is initiated, at least according to the calculation, can be as high as 13%. And that's the point at which carbon bonds tend to break in this particular simulation. So when this paper was, these findings were reported a couple of months ago in Science, in an introduction to this article, our article, Professor Javier Lorca from Madrid, he presented this figure in a perspective which was very interesting. So the maximum strength, tensile strength, that has been achieved in one-dimensional carbon, which is carbon nanotube, is of the order of about 100 gigapascals. In 2D carbon or graphene, The maximum strength that has been shown is of the order of up to 120 GPa. In our experiments in nano needles, the maximum strength in 3D that we demonstrate is of the order of about 100 GPa. And this is an interesting way to look at this. There are a number of potential applications of these kinds of effects. There is an entire field called nitrogen vacancy clusters, where you can create a vacancy with nitrogen, and that has unique optical and optoelectronic properties. And there is a whole community of physicists working on this in diamond. You also have diamond as a biocompatible material being used or being studied in research for biosensing, bioimaging, and drug delivery applications. Because diamond is also an electronic material, there is a significant opportunity to change band gap as long as you can induce elastic strains through so-called elastic strain engineering. And Professor Zhu Li at MIT and Professor Ting Xu at Georgia Tech have been working on the concept of elastic strain engineering from different points of view. So rather than chemically changing the elastic strain so that you can change the electronic as well as optoelectronic properties of diamond, there is an opportunity here to mechanically induce strains without chemistry, without changes to chemistry, whereby you may be able to achieve a similar effect. It is being thought that the maximum strain that, at least the minimum strain that you need to achieve this is of the order of 6 to 7% tensile strain. And we show here that in certain cases, you may be able to achieve as high as 9% strain. So this is yet another area that is potentially there is a lot of opportunity to explore possibilities in diamond with phenomena that one sees only at the nanoscale. So from that, I want to move to my second example. As we all know, everybody in this room has been working on aspects of this for a long time. One of the challenges that we face in material science is to design engineering materials where either through grain refinement or through processing conditions or through composite strengthening, etc., where we significantly increase the strength of a material, something else gives. And from a mechanical structural perspective, what gives usually is ductility, damage tolerance, fracture toughness, and fatigue properties. So is there an opportunity to create various strategies so that we can increase the strength significantly, but at the same time, at least try to protect a significant fraction of ductility, fracture toughness, and fatigue resistance, and in the process, make sure we have enough damage tolerance and tribological resistance of the material for surfaces. And this has been a topic of research for a long period of time. And of course, I want to highlight a number of phenomena that have been identified by many people that happen only at the nanoscale. Professor Jian Liu, our conference chair, and his colleagues have been working on a particular type of structures where you can induce twinning through mechanical means here in Hong Kong. There are other techniques that have been proposed. So I was in Doha in Qatar about 4 years ago. From our hotel room, we looked out the view, and there was a nice building, and my wife said, "Isn't that a beautiful architectural design?" And my first thought was, that's a very nice twinned microstructure, being a material scientist. So this is an example of a macro twin. Professors Lei Lu and Kei Lu in Shenyang have been working for the last 12 years or so in creating various strategies of inducing nanotwins which show unique properties. And some of their work showed that perhaps we can use nanotwins not only to significantly elevate strength, but also to preserve ductility. So about 9 years ago, Lei, Kei, and I looked at some of their results and some of other people's results in the community and try to identify criteria, minimum criteria that are required to ensure that we have the opportunity to maximize strength while preserving ductility. What are the requirements? We identified 3 requirements. You need to create internal boundaries that at least have initial coherency, mechanical coherency with the surrounding matrix. You need to have thermal and mechanical stability of the boundaries during mechanical loading, whether it's monotonic loading or cyclic loading, at room temperature or at elevated temperatures. And then in addition to that, there is something unique about the nanoscale, things that you don't see at the micro scale. At the nanoscale, if the internal boundary feature size is typically finer than 100 nanometers, then you have an opportunity, if all 3 conditions are satisfied, you have an opportunity, at least in theory, to create a structure that has increased strength and it has the potential for reasonable ductility. And of course, these specimens have been manufactured using techniques where we cannot create very large structures for very large structural components, at least not yet. So in the article in 2009, we looked at the effects of these, and here is an example of a typical microstructure that has been produced. On the left-hand side, you have, this is copper, very finely twinned material, where the twin size is of the order of a few tenths of nanometers, a twin spacing, lamellar spacing. The middle one shows something on the order of 70 or 80 nanometers. And on the right-hand side, you see a material of the same grain size, but essentially no pre-existing twins. So if you compare the 3 cases, obviously with a very finely spaced twins, you get the highest strength. You also can have the opportunity to get higher ductility and even some beneficial fatigue properties. But there are other artifacts of this. The activation volume of these materials is very different than conventional materials. And the other interesting result that comes out of this is the twin spacing in these nano-twin microstructures has an effect that's very similar to grain size effect in nanostructured materials, nanostructured metals. And so this is an example of one strategy that has been used among many, and I'm not going to go through all of these strategies. But one of the problems with this is, first of all, you don't get enough of a big specimen to do mechanical loading that is required, minimum specimen size that's required to do a valid fracture experiment or a fatigue experiment. So now let's see what nanostructured materials do, how they behave when it comes to fatigue, which is one of the most critical practical applications and one of the most challenging as well. So this is a classic SN fatigue curve that you would see, and here is an effect of grain size on SN fatigue life, as well as a number of cycles to failure and the fatigue endurance limit. So if you have a conventional microcrystalline material, this is nickel, a pure nickel. If you have microcrystalline nickel of a grain size of 10 micrometers or so, you get few hundred megapascal endurance limit, approximately 40 to 60% of the yield strength or the tensile strength of the material. When you go to microcrystalline to ultra-fine grain material, when say the grain size decreases to about 300 nanometers, your endurance limit increases by more than 50%. If you now go from ultra-fine grain to nano-grain material, where the grain size is of the order of 30 nanometer, this is electrodeposited nickel, and what you find is that the endurance limit still increases. So in high cycle fatigue, which primarily captures the life to initiate fatigue cracks, you get a beneficial effect of the high strength because of grain refinement in a nanocrystalline material. But then, if it's strain control fatigue, you will see that there is almost no data in the literature. There is very little data that's done with large specimens because specimens aren't large enough to do a valid cyclic deformation test by controlling strains. So when you go to low cycle fatigue, you run into the problem that the beneficial effects of grain refinement begin to disappear. And the same thing happens in the case of, if you look at nanostructured materials, that's on your right-hand side, that shows data in nanocrystalline nickel, ultra-fine grain nickel, and microcrystalline nickel. So what is beneficial for high cycle fatigue is actually not so good for fatigue crack propagation, especially at low crack propagation rates in the near threshold regime, where you have conventional coarse grain materials perform much, much better than a nanocrystalline material. We can try to overcome that by tricking the material by introducing initially coherent internal boundaries at the nanoscale, which are also thermally and mechanically stable. And that's what is shown on the left-hand side. So for 3 different nano-twin cases, so you have twin spacing of 30 nanometers, 85 nanometers, and 450 nanometers. This is work done in collaboration with Lei Lu and her student in Shenyang, and my PhD student, Aparna Singh at MIT. And what you see here is that when you introduce nano-twins, there is an opportunity not only to preserve ductility while increasing strength, there may be an opportunity also to provide some improvement in fatigue crack growth resistance. The problem remains that you cannot make these specimens in large quantities with enough thickness for a structural component where fatigue becomes an important criterion. So if that is the case, can you trick the material further and do things that are possible only because of nanoscale features? So let's see if we can do this. For this, we resort to graded materials as a strategy. And I'm going to show some very recent results, again in collaboration with Lei Lu and her team. But before going to that, I want to give a little introduction to what has been done by different groups in different mechanical properties with respect to graded structures, so that we can try to apply what we know for the last 20, 30 years to nanofield and try to see if we can improve the properties. So starting in the late 1980s, primarily through leadership from the Japanese materials research community, there were a lot of international conferences that were held, and a lot of very interesting work came out of it at that time. Then there is a lot of literature survey done by many people, and I'm particularly grateful to Professor Andreas Martensen in Lausanne, at EPFL Lausanne. We spent about 2 years in the late 90s summarizing the field and summarizing certain strategies in a monograph called Fundamentals of Graded Materials, which was published by the Institute of Materials in the UK in 1998. Out of this emerged some strategies that I want to walk you through. Now we can try to apply them to nanostructured materials. So the first piece of work that systematically in a scientific way demonstrated the benefit of nanostructured materials was in the late 1990s in ceramics. This is some work in collaboration with Professor Nitin Patture, who's now at Brown University, who at that time was at the University of Connecticut in Storrs. Nitin and I had a number of joint students who were looking at ways in which we can create an elastically graded material that had no plasticity. So here is an example of a particular system. We take silicon nitride, fully dense silicon nitride, and then we take Cylon glass on top of it. We melt the glass, and we can dope the glass in such a way that the coefficient of thermal expansion of Cylon is very similar to the coefficient of thermal expansion of silicon nitride. When you melt it, the glass diffuses into the silicon nitride substrate. Of course, glass has a Young's modulus of 110 GPa, and silicon nitride has a Young's modulus of about 300 GPa. So because of the diffusion, there is a continuous variation of Young's modulus at the surface of 110, about 200 GPa, 220 GPa, because it's part glass, part silicon nitride, to a depth of about 400 micrometers, where the Young's modulus is about 300 GPa. So that's the microstructure that you create. Now you take this microstructure, and then you take a spherical indenter, And then you do the following experiment. You take just silicon nitride, monolithic silicon nitride, take the spherical indenter, you push it and indent it onto the silicon nitride, you will get classic Hertzian cone cracks as expected for a brittle material. You do the same thing for glass, you will get exactly the same thing. You take a homogeneous material of the same composition as the surface composition of the graded material. Again, if it's a monolithic composite, then you will get the same Hertzian cone crack. But now if you do the experiment in a graded material, you completely suppress the fatigue crack during normal indentation in this elastically graded material, which has no plasticity. So that was a very clear demonstration. So here is the picture. On the left-hand side, if you take pure silicon nitride and you have no gradient, you get a classic Hertzian cone crack. But if you grade the material, the one that I've shown at the top figure, and you do the same indentation, you completely suppress. This is macro indentation. You completely suppress this. So we showed this in aluminum oxide, silicon nitride, several other ceramics. You can also show a similar effect in frictional sliding. So in collaboration with a student in Sweden that I co-supervised with Professor Peter Gudmundsson at the Royal Institute of Technology in Stockholm, we showed the same effect for elastically graded materials in frictional sliding. And Professor Patture and his team did further work on this in a variety of graded ceramic materials. And then a few years later at MIT, Ming and I had a joint PhD student, In-Suk Choi, who's now at Seoul National University in Korea. We looked at a plastically graded material where there is no elasticity gradient. So this is just the opposite of this. So you have no change in elasticity, only plasticity gradient. So we create a surface layer, and this is using some material that we produced at MIT in collaboration with Chris Shu. So we have a surface layer that's about it's about 20 micrometers thick, and you have it's a nickel tungsten nanocrystalline alloy. It has a grain size of about 90 nanometers. And then you have a small homogeneous layer of nanocrystalline material, and then you have a copper substrate. And then we do the indentation work. And then we found the following, that when you indent a graded material as opposed to any of the homogeneous materials, including the composite of different compositions, you find that the evidence of ductility in an indentation test, which is the pileup around the indenter, is the greatest in the case of graded material because of the way you distribute the loads during indentation into the substrate for a particular mechanism. So this gave us an opportunity to look at plastically graded materials with nano gradients at the surface. And here is the result that we found about 10 years ago. So what is plotted here is the pileup height over the base height, HP over HR, as a function of microstructure. This is just the nanocrystalline material only, coarse nanocrystalline material, and graded nanocrystalline material. This is experiment. This is finite element simulation of the behavior. In all three cases, we find that the graded material has the most superior response in terms of indentation response, with one indicator of ductility, which is how the material is able to pile up. So the moral of the story in all of this, whether it's an elastically graded material or a plastically graded material, you have the opportunity to trick surfaces to do things that you may not be able to do in a conventional way. This is where 3D printing, at least in principle, provides an enormous opportunity for design purposes. So subsequent to this work, in the last 10 years, a number of groups in the community have published papers in various forums showing the possibility of creating graded nanostructures with which ductility strength combinations can be optimized, homogeneous versus graded nanograin structures, etc. This particular figure is taken from a paper by K. Lu. So I want to finish with just two thoughts on this, one thought to finish this and a final example. This is some recent work in collaboration with Lei Lu. on how we can trick a material that has very poor fatigue response by creating a nanoscale surface layer, but in a large specimen. So here we have many millimeter size specimen, which is microcrystalline copper, but we create a graded layer, an ultrafine layer, and a nano layer at the surface. And then we mechanically fatigue it in cyclic loading at room temperature. As we mechanically fatigue this, we find that over a course of time, just as it happens in any microcrystalline material, there is a continuous change in microstructure. In traditional materials, you form dislocation networks, dislocation dipoles, veins, persistent slip bands, which cause intrusions and extrusions, etc. In the case of copper, which is surface graded, you have an opportunity to change this dramatically. So let's see what happens. In the as fabricated condition, you get nanoscale. The scale here is nanometers. You get nanoscale microstructure. If you go deep into the material, you get microcrystalline material. But after some period of cycling, the microstructure homogenizes, and as a result, you get nearly uniform microstructure of roughly comparable grain size or cell size through the thickness of the material. And that leads to some really unique fatigue properties. So for example, this is before testing. You have a very small grain size at the surface. As you go into the surface, you have coarse grain microstructure. After a few hundred or a few thousand cycles, depending on the loads that you put in, you get a much more homogeneous microstructure. This is very consistent with work that was done 50 years ago in just pure polycrystalline copper by Campbell Ladd and co-workers, where initially if you start with a annealed microstructure, you get strain hardening. If you start with a cold work microstructure, you get strain softening, but the final state is identical. So what is the benefit of this? For crack initiation, the endurance limit, stress amplitude normalized by strength in terms of reversals to failure, if you look at ultra-fine grain, coarse grain, or fine grain and graded, coarse grain graded, this is the endurance limit curve or stress life curve. But when you have a surface nano gradient, this is the best response of them all with respect to stress life fatigue. If you go to strain life fatigue, of course you have, this is stress life fatigue, this is strain life fatigue. If you add that, you get the total response. The transition is called the transition life, which is denoted by 2NF with a subscript T. So this indicates the optimum combination of high cycle and low cycle fatigue, stress controlled and strain controlled fatigue. So if you now plot fatigue limit as a function of transition life, conventional materials are here, but the graded nano grain material, you want to be in the top right, and the graded nano grain material has the best property of them all. So let me conclude with a very brief video on the implications of nanoscale in the biological systems. So this is in collaboration with Professor Tony Huang at Duke University, Dr. Yoel Sadowski, who heads the McGee Women's Health Research Institute in Pittsburgh, and my collaborator, Dr. Ming Dao. So what we do is the following. If you take a liquid fluid sample from the human body, whether it's a blood sample, placenta sample in pregnant women, or saliva sample, for example, can you isolate the smallest nanoparticle that you can find, which is typically an exosome or a vesicle? Can you isolate it in such a way that in the process of isolating it, you don't introduce any artifacts? Once you isolate it, you can do all kinds of analysis for disease diagnostics, continuous monitoring, and in some cases, in the case of cells, you can do cell culture with this. So this is the so-called rapidly evolving area of precision medicine and liquid biopsy for disease diagnostics and a variety of other purposes, including monitoring during pregnancy and so forth. So the technique that we use is the following. It uses standing surface acoustic waves. So what you see here is a device that was built to study this. This is 10 US cents. It's a dime, and it's a really small device. And we have two interdigitated transducers. These are the things that we have in our cell phones. So using a small battery, we can create a sound wave, which is a standing surface acoustic wave. And the principle behind this is very similar to what you find in ultrasound for pregnant women. And we know ultrasound is very safe for the human body. So it sends a sound wave, and if there is a microfluidic device in which there is a fluid flowing and particles are flowing in this, the sound wave causes a radiation pressure. So if you have two particles of the same size but different material properties, the stiffer particle will be separated differently, will have a different radiation pressure than the less stiff particle. If you have two particles of the same material but different size, the larger particle will have a larger radiation pressure compared to the smaller particle. So in any case, we can create different radiation pressures, we can separate them. We found that we can do that with an efficiency of about 98%. So then we thought, if we can do this, can we take a whole blood sample and look at cancer cells versus healthy cells? The cancer cells will have different radiation pressure, and therefore we can separate the cancer cells from healthy cells. So we took a cultured cell line, we spiked the concentration of cancer cells, and the next video shows. So the top, we do the same device. Cancer cells go one way and healthy blood cells go another way. And we did a study with 3 patients who had breast cancer in Hershey Hospital in Pennsylvania, and we were able to successfully isolate the cancer cells, 1 in 100,000 cells that's cancerous from the samples from the patient. So this is my last slide. I want to show what you can do with nanoparticles in whole blood. So this is essentially the technique. We take blood, whole blood, and we put it into a microfluidic device that has 2 interdigitated transducers. We create the acoustic radiation pressure. In the first phase, you remove all the red blood cells, the white blood cells, the platelets, etc. And then the smaller particles come here. We move all the vesicles, etc. out and keep only the exosomes. Exosomes are typically 40 to 130 nanometers in size, and they are the cargo that carry important information about physiology, health, and disease. They also carry other genetic information. So that's the goal behind this. Let me show the video that captures this.
Microfluidic device includes 2 subunits, each containing a pair of slightly tilted transducers. When sound waves produced by these transducers encounter one another, they generate a series of pressure nodes. Each time a cell or particle flowing through the channel encounters a node, the pressure guides the cell particle in a particular direction to isolate it and ultimately remove it. In the first unit of their device, there is a lower driving frequency, which isolates larger particles such as red and white blood cells and platelets. The second unit has a much higher driving frequency and therefore is able to separate the smaller nanoparticles and isolate the exosomes from the remaining blood. The new method takes less than 25 minutes to process as compared to hours or even days using a centrifuge. Microfluidic device.
So let me conclude. Nanostructured and nanoscale materials display unique mechanisms, as we have seen in 3 or 4 examples that we just described. There are a variety of potential applications, from 3D printing, where we can print on the surface different particles mixed with ultrafine and microparticles, a variety of MEMS and NEMS devices, graded materials design, bioimaging, biosensing, drug delivery, diagnostics, nanomechanical resonators, data storage applications, and more broadly, elastic strain engineering for electronic and optical applications. In fact, I'm very optimistic about the possibilities that this field provides, especially since there are a lot of young people in the audience. There is a tremendous opportunity in so many different fields where there are mechanisms that have been identified at the nanoscale, either with nano microstructural features or overall nano dimensions of a material that are not seen at the higher scales for a variety of these applications. Thank you.